last night. It didn't do anything else.
Didn't you?
No.
This is an outrage. I will speak to those people.
Little birdie said you set up the L.
Yes, what should you do it already?
It's not time to start.
Please. Don't worry, next time.
I remind you, last time we started talking about momentum, what is momentum? It's mass times velocity. I think of it physically as a measure of how hard it is to stop something that's moving. Why is it important to us? Largely because of the law of conservation of momentum. Momentum, the momentum of a system, that is to say the sum of all of the momenta of the bits and pieces, is conserved the same after the process as it was before, provided that no relevant external forces are acting. I'm sorry about the word relevant there, but I have to stick it. We're going to do collisions on this air track, for example, and we're going to imagine that there are no external forces acting when those two things bump into each other. And somebody is going to say, wait a second, how about gravity? Yeah, that's right, but that's acting down, and there's a normal force that cancels it that's acting up. Those forces are external forces acting on the two carts, I agree, but they're not relevant to the process. The process is happening in the horizontal direction. Or there are other circumstances where the process happens so rapidly that external forces don't have a chance to contribute to anything. Again, they would be irrelevant in this sense. I think next Monday, when I come to a more formal derivation of the law of conservation of momentum, it will be clearer exactly what that word relevant is in there. But I have to slip it in because otherwise a lot of the applications, somebody is going to object there wasn't an external force acting. But I think it's pretty clear in context whether it was relevant or not. The classic application of conservation of momentum is to collisions. I take that word in a sort of broad, very broad sense to mean two objects that interact with one another, either that they interact with one another very quickly, so even if there are external forces, they don't have a chance to do anything, or else they're completely in oscillation so that there are no external forces in the first place. But a collision is just an interaction of two things, or more than two things perhaps. The explosion of a stick of dynamite, actually you probably don't think of it as a collision, but in a sense it was. Originally there was some hunk of stuff, and later there's a bunch of shrapnel that's flying off. If I had done it in the other direction, a bunch of things fly together and then they stick together as a package, I think you'd agree that that's a collision. Is a collision in the other direction also. Or for example, the third owl on the homework on the owls for today, that was in a way a collision process. Do you remember what that was? There was a
Railroad car.
supposedly a completely frictionless railroad car. I didn't know about that. And there's some turkey that's standing on here, and the whole thing is going along at a speed, I think it was called W in the problem. So the cart has a mass M, and the guy has a mass little m, and he's just standing there for a moment. So there's this before And the scene afterwards, he starts walking down the cart so that he's now walking along, and they specified his velocity relative to the cart. So suppose that he comfortably walks at 3 miles an hour or something like that. That's relative to whatever he's walking on. So this would be relative. That was given to you. And the cart, meanwhile, is going to be going off at some other speed. Let's call it u. And the question is, what is that final velocity of the cart? U, I believe that's the way to put it, Tom. Is this a collision? Well, I guess not in the usual sense of the word, but it is an isolated interaction between two objects, a man and a cart. They were both moving along together in the first instance, and afterwards they're moving at different velocities. That is, in the more generic sense, an example of what I would call a collision. Right, it's cool. The word. How do you solve this problem, by the way? A couple of people have asked me to comment on this one. I think the difficulty was only because they specified the relative velocity instead of the actual velocity relative to the ground. They had given it relative to the train, and so there's some question about how to handle that. Well, this is a straightforward conservation of momentum problem. The initial momentum was the total mass, train plus guy moving at velocity w. That was the original momentum. And the final momentum, P final, is, well, there's the train, m, and it's now going at speed u. And there's the guy, and the question is, what is his speed now relative to the ground? We know what it is relative to the train, but what is it relative to the ground? Suppose he wasn't walking at all, then his velocity relative to the ground would be u. Suppose that he was walking just very, very slowly, then his velocity relative to ground, I guess, would be u minus a hair, isn't that right? If he's walking at a good clip, v relative, what is his velocity relative to the ground? I say it's u minus v relative. Make sense? His velocity relative to the ground, if the train is going u and he's going in a backward direction relative to the train at speed v relative, then his velocity relative to the ground is u minus v relative. Let's check that. These things are always conceptually a little difficult to think about, but one good check. Suppose that he was walking at speed u in the backward direction, and the train is going to the right at speed u. How fast would he be going relative to the ground?
0.
Not at all. 0. Does that come out here? Yes, it does. What if he was walking faster? Relatively, suppose that the train was going at 2 miles an hour and he's walking at 3 miles an hour to the left. Well, big deal. Then his velocity actually is going to come out negative relative to the ground. That would be when this number is larger than this number. I put all of the velocities at positive to the right, and if it so happens that v relative is bigger than u, I don't know whether it was on this problem or not, then this would turn out to be a negative number. Now, how do you solve the problem? What we were looking for here, I believe, was u. Use conservation of momentum, set the initial momentum equal to the final momentum, and solve for u. Make sense? So, is that a collision problem? Well, I'm not going to quarrel with you that you said it's not a collision problem, but it is an interaction of two objects with no external forces that are relevant to the problem. There are gravity and normal force, of course, but no relevant external forces acting, and the way to handle it is conservation of momentum. A collision process, either because by its nature it happens so fast that no external forces can act, or because it truly happens in isolation and there are no external forces, for either one of those two reasons, momentum is always conserved. I say momentum is always conserved. In fact, my advice to you, what I do is if I'm taking an exam or something like that, I see the word collision in the problem. Immediately I write down conservation of momentum before I read anything more. Even if there's something that vaguely smells like collision in there, I write down conservation of momentum right away because that's always going to be conserved in the collision process. How about kinetic energy? Is kinetic energy always conserved in a collision process? No, it is not. Or rather, sometimes it is and sometimes it isn't. So, my advice when you see a collision problem is write down conservation of momentum immediately, and then scan the problem a little bit more closely. Look at the wording a little bit more closely to figure out whether kinetic energy is also conserved. I like to classify collisions into 3 types. One, what I call sticky collisions. The extreme example would be, for instance, 2 lumps of clay that are fired symmetrically at each other. Imagine they're both exactly the same mass, and they're fired with the same velocity at each other, and those 2 lumps of clay stick together. So there's a scene before, and the scene afterwards is a single lump of clay, and by conservation of momentum, because this was symmetrical, the momentum, total momentum before was 0, total momentum's got to be 0 afterwards. That lump is just sitting there. There is an extreme case of a sticky collision. Just 2 things come together and they stick. What happened to kinetic energy in that problem? Kinetic energy? Yeah. Kinetic energy? Yep. Kinetic energy? No. Kinetic energy decreased in a sticky collision. Typically, it was converted into heat. Maybe sound and light and all kinds of other things. By the way, watch out for the signs here. I said that the momentum, the initial momentum was 0. Why? Because this is mv to the right, this is mv to the left. Add the 2 together, one of the velocities is negative, the total momentum is 0. Then I came to do conservation of energy, and I said 1/2 mv squared, 1/2 mv squared. I added the 2 together, and I got a positive number. What's going on here? Why didn't the kinetic energies cancel the way the momenta do? Momentum is mass times velocity. The velocity can be either positive or negative, or in general can be pointing in either direction. Kinetic energy is 1/2 mv squared. It's not a vector, it's just a number. Moreover, it's a number by its nature that is always positive. You can't have negative kinetic energy because it's mass times the square of a velocity. So kinetic energy is always positive. There's no opportunity for 2 kinetic energies to cancel each other. Momentum can be positive or negative, and there very certainly is the possibility of cancellation of 2 momenta. So watch out for that. In the case of momentum, you've got to be careful of the signs. In the case of kinetic energy, you do not. It's always positive. So here's a case in which momentum was conserved, as it always is in a collision, but kinetic energy clearly decreased. Most sticky collisions are not sort of 100% sticky like that extreme case. In fact, I think I did an example last time in which a bullet plows through a block of wood and it comes out the far side with a somewhat reduced velocity, and meanwhile the block of wood is moving along. That also I would call a sticky collision. Some kinetic energy was lost in that process, and the block was heated up somewhat as the bullet plows through there. So that's a partially sticky collision. Here's a very sticky collision. So that's one type of collision in which kinetic energy decreases. Second type, I call them explosive. I'm saying I because this is my personal list here. Other people don't do it this way, but they are. An explosive collision, extreme case. Here's an example. Suppose that I had 2 carts and they're stuck together with some kind of a compressed spring. You could do this on the air track. actually. Stick these together, put a compressed spring between them, and then tie a little piece of string between them so that they're just sitting there, but there's this compressed spring that's holding them together. And then I take a pair of scissors and snip the spring, snip that string, and the spring fires the two out in both directions. So originally the two are at rest, and then the spring gives way, and one's going this way, and one's going this way. What happened as far as momentum is concerned? 0, 0, exactly the reverse of this process. What happened as far as energy, kinetic energy is concerned? Zip here, converted into kinetic energy here. So kinetic energy increased. Kinetic energy increases in an explosive collision, in contrast to a sticky collision. Where did that kinetic energy come from?
Potential.
Well, it was potential energy stored in the spring. In that instance, another case, you might have a stick of dynamite there that blew up and fired the two apart. Okay, in that case, it came from chemical energy. But the point is, it came from some other form that was stored in the original system and was converted into kinetic energy in the course of the collision. Yeah, collision. Is this a collision? Sure, in the sort of generic sense. Originally there was one lump, finally there are two lumps that are moving. But it's sort of a generic kind of collision. If this is a sticky, is a collision, this is just the reverse of it. The third type of collision is the one in which kinetic energy is conserved. For this there is a code word. The word is elastic. That's a code word in this business. It just means kinetic energy is conserved. But nobody on an exam wants to say, in this collision, kinetic energy is conserved, because it seems like they're telling you how to solve a problem. So they say, this collision was elastic. I mean, you're just supposed to know. Elastic means kinetic energy was conserved in this collision. By the way, some people, including your book, I think it's a stupid language, but will call the extreme case of a sticky collision, when the two things are literally stuck together after the collision, they'll call that completely inelastic. It is inelastic, I agree, that kinetic energy is not conserved, but that language sounds funny to my ear, because elastic means kinetic energy is conserved. Inelastic means kinetic energy is not conserved. So when they say completely inelastic, they're saying kinetic energy is completely not conserved. What on earth does that mean? Well, the way they're using it is they mean the two objects actually stuck together afterwards. I don't know why they don't just say that. So those are the three different types of collisions that we encounter: sticky, explosive, and elastic, categorized according to what happens, not to the momentum, because that's conserved in all cases, but what happens to the kinetic energy. When you see a collision problem, my first thing that I do is scan it to see whether I think that's an elastic collision or an inelastic collision. Sometimes they say an elastic collision is like the collision of two billiard balls on a billiard table, or collision with really good bumpers here on the air track or something like that. An elastic collision is a nice sort of perfect collision or something. I don't know. No energy lost in the process. So now I'm going to run a string of examples, every possible type I can think of. Elastic, sticky, inelastic, two-dimensional, one-dimensional, combinations with other things. I have a whole arsenal of examples here, and I'll run through as many as I can today and then pick up the rest on Monday. So, example one. This is going to be a sticky collision. So kinetic energy is not going to be conserved. The collision itself is going to be stupidly easy, but I want to look at the energy balance here. So I imagine that I have two carts. One is 2 kilograms, and it's going at 6 meters per second. And it hits another cart here that's 2 kilograms, and it's just sitting at rest. So here's the scene before. If you like, you can imagine that this is happening on the air track here. Only instead of using the bumper side, I'm using the Velcro side, so they're actually going to stick together afterwards. And I would have a composite object whose mass is 4 kilograms, just the sum of those two. And I would like to know how fast is this thing going to be going after the collision. Simple, very straightforward problem in conservation of momentum. Yeah.
Should we choose a positive x direction or when
Yes.
we write the formula?
Yes, absolutely. So here's the positive direction here. For a moment, the problems are going to be one-dimensional problems, and all the velocities are going to be pointing in the same direction.
Okay.
So I can afford to be sloppy, but you're absolutely right. I should get in a better habit, because later on it's going to be critically important to be sure that you know which direction you meant is positive. So there we go. How do we solve this problem for the final velocity? Conservation of momentum. 2 mass times velocity is 6 is equal to the final velocity, the final mass, that's 4 times the velocity v, the thing I'm trying to find. So this is 12 equals 4v, divide the 4 into 12, you can get 3. So v equals 3 meters per second is the velocity that that composite cart is going to be going off at. But that's not really what I was interested in. I want to explore what happened to kinetic energy in this case. K initial, well, this one doesn't have any kinetic energy, it's just sitting there at rest. K initial was 1/2 the mass here, 2 times the velocity squared, 6 squared. The 2's cancel, and I get 36 joules. That was the initial kinetic energy in this problem. What's the final kinetic energy? Kf is 1/2 the mass, which is now 4, times the velocity, which I just calculated is 3 squared. That's 2 times 3 3s are 9, is 18 joules. So, was kinetic energy conserved in this process? No, it was not. It was originally 36, it was finally 18. I lost some kinetic energy. Is that kind of what you anticipated? You should have, because this is a sticky collision, and you should expect in a sticky collision, kinetic energy is actually going to decrease. Where did it go? It went into heat. You shove a thermometer into those carts and you'll find that they're a little hotter than they were before. Okay? So there's typical sticky collision in one dimension. Okay, let's do an elastic collision in one dimension. I'll do it for you first. Watch very closely what's happening. I got 2 carts on here, right? Okay, I want this one to be at rest, and I'm going to fire the other one at it. And it's got nice springy bumpers, so this is supposedly elastic. Let's do that again. It looks like the track isn't exactly level because it's kind of go down a little bit. But watch it, and watch, see if you can pick out what's a remarkable feature of this. What did you notice?
Stops.
This one stopped dead in its tracks, and this one takes off with the velocity that this one originally had. Amazing. Do that again. Why is that? What do we have here? I had cart 1 with mass m, and it was going along with speed v, and it hit cart 2, which was also mass m and at rest. So here's the scene before. And what happened? Well, let's pretend that I didn't know what was going to happen. I have the one that came in. We'll say that it's going now at a speed u, and the one that it hit is going at a speed w. And it's my business to find out what those u and w are. V is presumably given. U and W are the unknowns. So that's what I'd like to find. And you and I kind of know, because we just saw it happen, that U is actually going to be 0 and W is going to be V. But pretend you didn't know that. Imagine that we're just calculating these two. How would the calculation go? Conservation of momentum. This is example 2. Conservation of momentum says mass times velocity equals mass times velocity plus mass times velocity. The m's conveniently cancel, and I could write this as a formula if I like for W. W is equal to V minus U. Remember, the unknowns are W and U here, so I want to eliminate one of them in favor of the other. And now the other piece of information that I have is that this was an elastic process, so conservation of energy says 1/2 mv squared, the kinetic energy of this one, none for that one, equals 1/2 mu squared for this one, plus 1/2 w squared for this one. 1/2 m cancels. And I get the conclusion that v squared is equal to u squared plus w squared. That's what conservation of energy tells me in this problem. Now let me stuff the formula I had here for W into this equation here, and I'll have a single equation in one unknown, W. Solve for that, then come back and put that into here, and I'll get, I'm sorry, one unknown, which will be U. I'll put that back in here, and I'll get W. Got the strategy? Let me warn you, by the way, this is an unbelievably simple elastic collision process, but you should know that you can get into nightmares of algebra with elastic collision processes. You never encounter anything more than a quadratic equation. So in principle, all the cards are at the table. It's very easy to write down conservation of momentum, conservation of energy. But fact is, if the numbers are ugly, you can get tangled up in some heavy algebra. So it pays to think very carefully when you're setting up a problem involving elastic collision. Make sure you're doing things efficiently. So I use conservation of momentum to solve for one of the two velocities. In terms of the other, I'm going to stuff that in here and get a single equation. So this says v squared equals u squared plus w squared, but that's v minus u quantity squared. Let me square that out. U squared plus v squared minus 2vu plus u squared. I see a v squared cancels on the two sides. The u squared I can combine with the other u squared and write this whole equation as 0 equals 2u squared minus 2uv. Or if I factor out the 2 and the u minus v. So 0 equals 2u times u minus v. Solution? Well, two solutions. What are the two solutions there? Two possible solutions for u. If u times u minus v has got to be 0, that means either u equals 0 or else u equals v. Be very cautious at this point. You're always going to get two solutions. Keep both of them because it's not always obvious which one is the one that you want. In this case, you can probably tell which one I want, but pretend you didn't know. I'm going to be very plotting about this. If u is equal to 0, then what is w? W is v minus u, so that would be w equals v. If u is equal to v, then what is w? 0. So, two possible solutions. Now I look back at the original problem and try to figure out which one of those is the right solution. And what the wrong solution is trying to tell me. what do I observe here? After the collision, this one better the hell be going faster than this one. Isn't that right? I mean, it's obvious. This one, since it's over to the right, better be going faster. So W has certainly got to be bigger than U. Make sense? If W is bigger than U, then this one's okay, but this one's no good. So this must be the correct solution. U is equal to 0, W is equal to V. The first cart stops dead in its tracks. The second one picks up the velocity that the incoming cart had and takes off with that. That's exactly what we saw on the air track. What does this other solution tell me? How would you read that? U equals V. That means this one, the one that was coming in with velocity V in the first place, is still going with velocity V. And W, the other one, is 0. That one is just sitting there. What's happened in that case?
Went through
It just passed right through, never touched each other. That was no collision at all. But was it consistent with conservation of momentum? You better believe it. It just kept on going. Nothing ever happened. Was it consistent with conservation of energy? Yes, of course it was. Nothing ever happened. So that had to emerge as a second route. All I was imposing was conservation of momentum and conservation of energy, and obviously no collision at all would certainly satisfy conservation of energy and momentum. So when you get to this point, even in a more complicated problem, the two routes, the two solutions you get, one of them had better be exactly the status quo ante, if you will, physically with the two just passing right through each other and never talking. But that's of course not the solution we want. The solution we want is the one that comes from the bona fide collision. But it's natural that that other route should have emerged because it does indeed satisfy both of the conservation laws, which is all that we have to put into the problem.
Is it possible for the second mass to be stuck somewhere, not move, and the other one to have a different, opposite direction? The direction of U velocity to be the other?
No. No, unless some external force was acting. So, suppose that I had my hand there or something like that, then, so this one absolutely couldn't move, and when this one comes in, it would bounce back, that's true. But then there was a heavy-duty external force acting. It was not just the interaction of those two. If it's just the interaction of those two, think about it, and it's elastic, those are the only two laws that you have to play with. They're going to tell you what are the possible solutions. It might have been the case that there were 600 solutions to these, and then you said, well, one of them is the thing bounces back or something. No, I'm sorry. This is always going to give you a quadratic equation. There are always going to be exactly two routes. One of them is the original situation, or if you like, one passes through the other without ever interacting. The other solution has got to be the one and only collision solution. It's astonishing, actually, in my opinion, astonishing that you can solve this problem at all. Because I never asked you, I never inquired what the force of interaction between the two was. It doesn't matter. There are only two possibilities here consistent with conservation of energy and momentum. One of them is the original situation, and the other is the only possible case. So in fact, it doesn't matter how these things bounced off each other, as long as it was elastic. It could have taken 45 minutes and been some complicated interaction, or it could have taken a split second and it'd just been a contact interaction. I don't care. As long as it obeys conservation of energy and momentum, this has got to be the final outcome. Very powerful. Well, suppose that I had two-dimensional collisions. Now, so far I've talked only about one-dimensional collisions. So now we're not dealing with carts on the air track, but billiard balls rolling around on a billiard table. In two dimensions, collisions in two dimensions, it's easy. Momentum is conserved in both directions. Both components of momentum are conserved, because actually conservation of momentum is vector, remember? So conservation of momentum really means conservation of the momentum vector in three dimensions. Actually, all three components would have to be separately conserved. we don't do a whole lot with three-dimensional collisions because they can geometrically be awfully damn complicated. But in 2 dimensions, on a billiard table or something, that we can analyze reasonably. Both components. Okay, I'm going to do an elastic collision and an inelastic collision in 2 dimensions. Which shall I do first? I'll do the fun one first. It's the 2-dimensional analog to this case here. This is the dessert before the meat course, but okay, I'm a bit rare. Example 3. Two billiard balls collide. Billiard ball collisions are a good example of elastic collisions, provided that you don't put too much English on them. You know, if you play billiards and you put lots and lots of spin on them, then that's more complicated because I got spin kinetic energy as well as just translational kinetic energy. So don't do that. Just nice, easy shots. Always hit at the minute. So 2 billiard balls collide, and they both have the same mass. Same mass because these are 2 well-manufactured billiard balls, and the target is at rest. So here's the scene beforehand. I have a billiard ball of mass m, and it's coming in with speed v. And it hits another billiard ball, it's just sitting there. What happens? It's not a head-on collision. Now, if it's a head-on collision, I've already done that problem. This is going to be an oblique collision. So that the 2 go off. One of them goes off like this. Let's say that its velocity is u, and the other one goes off like this, and its velocity is w. So there's the scene after. And I want to know what are those final 2 velocities. I give you the initial velocity, I give you the 2 masses. I'd like to know what are the final velocities. Actually, I can't determine that because it would depend on exactly where the first one hits the second one. But I can tell you some fantastic information about this process just by using conservation of energy and conservation of momentum. So what does conservation of momentum say? The initial momentum, now 2 dimensions, vector, m v, the vector, is equal to the sum of the momenta afterwards. M times u, the vector, plus m times w, the vector. How about I cancel those m's? V is equal to u plus w. That's what conservation of momentum says. How about conservation of energy? Because this was an elastic collision. Conservation of kinetic energy, of course. 1/2 m times v squared. No vector sign, this is just the magnitude squared, is equal to 1/2 m u squared plus 1/2 m w squared. Cancel 1/2 m. V squared is equal to u squared plus w squared. So conservation of momentum says that the sum of the 2 final velocities as vectors, they add up to the initial velocity vector. And conservation of kinetic energy says that the sum of the squares of the outgoing velocities is equal to the square of the incoming velocity. Big deal. Actually, very big deal. Let me show you what you can do with that. What I propose to do is take the square of the first of those equations, the one that came from conservation of momentum. Squared. So I get v squared equals, well, it's v dot v if you like. That would be the length of v times the length of v times the cosine of the angle between them, but the cosine between something in itself is 1. So this is equal to v dot v. So let me calculate it using the fact that that's u plus w dot u plus w. Now, if I do this dot product, the first term is u dot u, which by the same argument is u squared. And then I get u dot w, and then I got w dot u. So that would be 2 u dot w. And the last term would be w dot w, which again is w squared. See how I did that? Squaring the sum of the two vectors, I get, it's just like multiplying out a binomial, except that the middle term, the cross term, is actually still a dot product here, u dot w. This I could have written as u dot u if I wanted to, but u dot u is simply the square of u, so why not write it like that? Well, this is equal to v squared. V squared is equal to that. But on the other hand, I know from conservation of energy that v squared is equal to u squared plus w squared. What do you conclude from the two of those? Oh, have I lost you?
That
Somebody
the
said it.
angle
U dot w is equal to 0. It's got to be. Well, if u dot w is equal to 0, what do you conclude from that? Somebody said they're perpendicular. Actually, that's right. Either they're perpendicular or one or the other of them is 0. But one or the other of them being 0 is the case that we already handled. That was the head-on collision. So that certainly is a possibility. Otherwise, u dot w is equal to 0, which means that u is perpendicular to w. The angle between those outgoing velocities is always 90 degrees. You've played too much pool, that's the problem. But actually, it is the case that if you hit the ball straight on, has anybody played enough to know that those two things, actually, they do come out at right angles to one another. They come out at right angles to one another unless you put a whole lot of spin onto one of them, in which case all bets are off, because as I said, then you can have energy dumped into rotational form as well as kinetic form. But if it's just a straight-on collision here, off-center collision, these things will go off at 90 degrees to one another. I don't know what the actual angle is, because that's going to depend on how exactly this hit, where exactly this one hit this. But this much I do know. However those two velocities go off, they'll always be at 90 degrees to each other. Fantastic. In fact, the two outgoing velocities are always perpendicular to each other. Actually, in a way, that also includes the case where one or the other of them is 0. If you say that 0, the 0 vector is perpendicular to everything, as mathematicians would say. The 0 vector is always perpendicular to everything. Then the single conclusion here is u is perpendicular to w in all instances. There's a danger in this, so I've got to put a warning. Because I've noticed in other times that I've taught this subject, is that this result is so striking that it sticks in people's minds. But watch out, because this actually, and the previous one, where the first one came in and stopped dead, both of those are very special cases of elastic collisions. Do not conclude that it's always the case that the final velocities are at 90 degrees to each other. What did this depend on? Both examples 2 and example 3.
Masses are the same.
Masses are the same. Second, target was at rest. If the other part, billiard ball had been moving, then they're not going to come out at 90 degrees. And third, it's got to be an elastic collision. So examples 2 and 3 have very beautiful, cute, I say cute results, but those cute results are very special. They pertain to the special case where I have a collision of equal mass particles, the target was at rest, and the collision was elastic. So don't jump to that conclusion for all collisions. It's a little too easy to remember that result. I'm going to do a more complicated problem involving an inelastic collision in 2 dimensions, but I think actually it would be more valuable for me to do a different problem. I'll save that one for Monday and do instead an example of what I call a compound process, because you're going to hit one of these on the hour for Monday. Example 4, the ballistic pendulum. This is an example of a large class of problems. You know, you may, if you're taking 173, you may do the ballistic pendulum in the lab. Do you happen to know? I think it would not have come yet. This is an ancient technique for measuring the velocity of a bullet. I imagine that I've got a bullet coming along here, and now hanging from the ceiling on a pendulum is a block of wood. And I fire the pendulum, fire the bullet into the block of wood. You have seen it? What happens? The bullet embeds itself in the block of wood. So here's the second scene immediately after the bullet hit. There it is, stuck inside. And now this block is moving over with a velocity, let's call it u. So the bullet came in with a velocity v. It hits a block of wood with a mass capital M. Immediately after the collision, the bullet is embedded inside that block of wood, and the thing is starting to swing. And then it swings up to some configuration like this, where it's up by a height h relative to where it was in the original instance. And what I do is I measure the height h to which that thing swings, or maybe you measure the angle theta to which it swings. And from that measured height h, or the angle, you're trying to determine what the velocity of the bullet was in the first instance. Why do I call this a compound problem? It's a compound problem because the way to think about it is to realize that there are 2 completely different operations going on here. First, there was a collision. Bullet hit block of wood. In that process, momentum was conserved. Was mechanical energy conserved? No, it was not. What kind of a collision would you call this, in fact? It's a sticky collision, sticky with a vengeance. This is what they call in the books a completely inelastic collision. That bullet's embedded in there. So the first process, collision, momentum conserved, but energy not conserved. Then there's a second process. This pendulum, with the bullet embedded in it now and going to the right at speed u, swings up into this final position. In that part of the process, is momentum conserved? Yes. No, it is not. How come? There's an external force acting on here. The horizontal component of the tension force is pulling back on that thing. Momentum is not conserved because the thing was going to the right at this point, and when it comes to the very top of its swing, it's no longer going to the right. Momentum was not conserved there. Why not? Because it was an external force acting on it over a long period of time. It had soaked up the momentum that it originally had. So for this process, momentum not conserved. But how about energy? Yes. This is one of the kind of problems that we dealt with before. Something is swinging on pendulum, you give it a hit, it's going at velocity v, it swings up, conservation of energy. But you see what my essential point is, to realize that there are two completely different operations governed by totally different laws of physics going on here. There's the collision process first, which does obey conservation of momentum but not energy, and then there's the swing, which obeys conservation of energy but not momentum. Realizing that, I think we can write down the answer very quickly. Conservation of momentum says mv is equal to m plus m, because this block now has some bullet embedded in it, times u. That would tell me what u is. U is equal to m over m plus m times the original velocity. Now I do conservation of energy over here. Originally kinetic energy, 1/2 m times capital M u squared is equal to
mg.
potential energy, mgh, actually m plus m, gh. The m plus m cancels, I get u squared equals 2gh. And now I would plug in what u squared is from the first part of the problem. That's m over m plus m squared v squared. And I can solve for v. So there's the velocity in terms of the height h to which this thing rose, and a clever way to measure then what the velocity of the original long bullet was. But the magic of these problems, and as I'll say, there's a whole class of problems like this, is to chop them into two separate pieces, typically conservation of energy for one part, conservation of momentum for the other. Third,